Hello and welcome to our next lecture. Today we're looking at the numerical implementation of the discrete Fourier transform, which is the fast Fourier transform. So to demonstrate the benefits of the fast Fourier transform and what you can do with this, I prepared this little notebook and a few test signals that we can play with. So the first signal we're going to play around is just a recording of somebody dialing a number on a touch-tone phone. Can you guess what numbers were pressed? Before we start analyzing the signal, let me explain how the touch tone is generated. Every time a button is pressed, two frequencies are emitted. So for example, if somebody pressed the number 2 and the frequency of 697 Hz and another signal with the frequency of 1336 Hz are emitted, this is how the equipment on the other end can recognize which button was pressed. The structure of the sound object in Mathematica is quite a complicated one, but Mathematica provided a few functions for us to extract the data from it. So the audio data command will extract the numerical data from the recording. There's also a few properties of this structure that are somewhat important to us, and the most important one is the sample rate. So this signal is generated with a sampling rate 8000 Hz, which means that the samples were created about 8000 times per second. So I'm going to extract the sampling rate. I'm going to look at the length of the sound data that we have, and L will be the length in seconds of the sound sample. So the sample rate is 8000 Hz. The number of samples is 16,000. That means that we have 2 seconds of recording. If I plot the sound signal as dots on the plane, then I have this huge mess of dots. So I have 10 digits were sent. If you listen closely, then you can probably recognize that the first 3 digits are the same. So if I compute the discrete Fourier transform, which is done by the command Fourier here, and I'd like to point out that this command works a little bit differently than the Fourier transform that we defined. It does multiply by e to the positive 2 pi I rather than negative 2 pi I. It has 1 over square root of n multiplier in front of it, but for us it's not really that important as long as the Fourier transform and the inverse Fourier transform work together. So the fast Fourier transform is computed, and if I plot the fast Fourier transform, then I can see that there's quite a lot of frequencies present here. And again, I'd like to point out that we only need to look at this half of the picture. You see the other half is the mirror reflection of this half. These are the negative frequencies that kind of migrated due to periodicity to the higher frequency part of the spectrum. These frequencies are not present in the signal. These are. So if I look at all of those frequencies, then I can't really see which frequency was emitted at what point. All of the frequencies are present here all at the same time. So in order for me to differentiate the digits, I have to zero out parts of the signal. And here's where I created this selector thingy that just multiplies parts of my signal by things that are close to 1 in the portion of the signal that I want to keep, and by things that are very close to 0 in the area where I want to zero out the signal. By the way, I made the selector to work so that it works in seconds, and if I want to select the second digit, then I probably need to select things that are very close to 0.25, and the second parameter is the spread of my selector, so 0.1 is the parameter that works very good. Selector is just a graph of the Gaussian that just very close to 1 at a particular time and very close to 0 everywhere else. So 0.1 is a very narrow selector, and this is the effect of this selector applied to my signal. So I kind of singled out the second digit that was pressed. So if I compute the fast Fourier transform of it again and plot it, then I actually see 2 distinct frequencies in the signal. Again, I'm going to ignore this and concentrate on the two frequencies I see in the part of the fast Fourier transform that's close to zero. Well, this is just a vector of samples from 0 to 16,000. So which ones of the samples correspond to which frequencies? That is something I need to clarify a little bit as to how to recognize which frequencies are in when all you have is just a number of samples. So if I have a signal with 1 Hertz, which means one sample every 1 second, then when I compute the discrete Fourier transform multiplying by things like e to the minus 2 pi I k over n times j, and the number omega k, that is 2 pi k over n, represents the frequency that I'm trying to sample here. So these exponentials are going to be periodic with the period 2 pi. So that means that if I sample with the frequency 1 Hertz, then the spectrum is going to be on the interval 0 to 2 pi, which is actually meaning that the spectrum is from minus pi to pi, because as I said, those higher frequencies are actually negative frequencies on the other end. So if I increase the frequency, and I say I have new Hertz frequency, well, increasing the sampling frequency increases the range of frequencies that could be captured by a signal, so it actually spreads the spectrum to minus pi times nu to pi times nu. So if I sample with the frequency 8000 Hertz, then my actual spectrum in terms of radian frequencies is going to be from minus 8000 pi to positive 8000 pi. And each one of those frequencies is going to be represented by the number omega k, which is this time is going to have a multiple nu in there. So let me visualize this interval from a minus pi nu to positive pi nu with the samples of the omega k for each k. So when k is 0, I am right here representing the 0 frequency. The right endpoint of this interval is going to be captured by the fast Fourier transform element with the index about n over 2, and then all of the other indices will be representing the negative frequencies. So if I have a kth element here, then this is exact k over n over 2 times pi nu part of the frequency spectrum that we can capture. So that means it's going to be 2 pi k nu over n when you simplify. But this is a radian frequency, therefore the actual frequency is going to be the radian frequency divided by 2 pi, so it is just k nu over n. And in the case of the signal that we have, it's k times 8000, that's the sampling frequency of the signal we have, and we have exactly 16,000 samples, so it's just k over 2, or k over the length of the signal that we captured. So this is why I am plotting this fast Fourier transform not with respect to k but with respect to k over L, because then the numbers that I see here actually represent the actual frequencies present in my signal. As you can see, both of the frequencies are below 2000, so I would need to plot it from 0 to 4000. So I need to plot first 4000 samples because the length of the signal is 2. So 2000 element here represents the 4000th sample of the fast Fourier transform. Now we can see the separation of the frequency a little bit better. You can see that I probably can get away with just 3000 samples, and I probably need to start from the 1000 samples on the other end. So now I can see a little bit better that this number here, that's 800. So this is about 780 right here, and this is about 1300 with the halfway to 1400, so it's about 1350 right here. And if I look at my table, then it actually, the 1300 is this column and 780 is about here. So I probably pressed the button 5. So the second digit was probably 5. Let's look at some other digits. So let's look at the digit. Let's look at the 7th digit. That is about 1.25 seconds. And let's compute its Fourier transform. As you can see, the frequencies are shifting a little bit. I still have about 770 right here, but now I'm very close to 1200 in the higher frequency. So that corresponds to the number 4 pressed. So the 7th digit was 4. Alright, so this is how we can use the fast Fourier transform to recognize frequencies present in the signal. There's another aspect to the fast Fourier transform that it can be used to clean up the signal, to erase some of the frequencies that we don't want in a signal. So here I have a recording that you may have heard in the past.
Houston, we have a problem.
As you can see, this recording is very noisy. And what I'm going to try today is I'm going to try to clean up the noise as much as I can. So again, I'm going to record the data of the sound samples in the SND list. Sampling rate here is 11,000 Hertz. So if I compute the Fourier transform of it, then these are the frequencies present in the signal. Again, note that the spectrum is completely symmetric, again, because the only frequencies that are present in the signals ending right about here, and then the rest of the image should be on the other side with the negative frequencies. So what I want to do is I want to erase those high frequencies, because this is probably where the noise is coming from, and the lower frequencies are the ones that where the voice recording is. So I'm going to multiply this Fourier transform by this function, which is 1 in the areas where I don't want to erase any frequencies, and 0 in the areas where I want to erase some frequencies. So I created a filter function that has two parameters, width and spread, which is the width of the frequencies around the middle that I want to zero out, and the spread is how soft this drop-off should be. So if I increase the width parameter, then I will be erasing more frequencies. And if I decrease the spread, then it's going to be a slower drop-off. So if I look at the fast Fourier transform and I zero out some of the frequencies, this is what I'm going to get. Just erased parts of the noise that are in the higher part of the spectrum. So if I'm going to generate, so what I'm going to do is I'm going to multiply my Fourier transform by this particular filter, and then invert the Fourier transform and use the real part of this Fourier transform to generate the sound.
Houston, we have a problem.
We can still hear some of
Houston,
the noise.
we have a problem.
So if I increase the width of the filtering, say I am going to make it 7. If I make it 7, then I'll be erasing more of the unwanted frequencies that I have in my signal.
Houston, we have a problem.
You can see that the noise is actually getting a lot quieter. It does affect the voice because the higher pitch parts of the voice are also erased.
Houston, we have a problem.
But the noise is going away. And I think at 9 is where
Houston,
the
we
noise
have a problem.
is almost completely gone.
Houston, we have a problem.
Yes, the voice sounds like somebody is speaking into the bucket, but that's the side effect of actually applying the filtering. Another thing that I'd like to demonstrate is that we can do the filtering without using the Fourier transform, because using the Fourier transform is quite an expensive operation. So what I'm going to do is I'm going to compute the inverse Fourier transform of the filter, since it's being multiplied in the frequency domain, then all I have to do is to take this inverse Fourier transform and do the convolution with the sound. So it seems like there's nothing here in my filter, but actually there's something happening at both ends. You can see there's non-zero values at one end and non-zero values at another end. I'm going to show you where the non-zero values are located. So you can see the first 30 elements from the convolution filter are non-zero, and the last 30 elements from the convolution filter are non-zero. So since all the rest of them are very, very close to zero, I'm going to shrink my filter to include only the first 30 and the last 30 elements. So the last 30 elements are kind of the mirror of the first 30 elements, and that's something that should be expected. And so I'm going to make a new convolution filter by joining the last few elements with the first few elements of my filter. So here I chose the first 72 elements because the size of my filter is 1372, so it just makes math a little bit easier. It's complex valued, but that's understandable because I'm taking the inverse Fourier transform of a real signal and it should be complex valued. So you can see, kind of put the filtering right in the middle of this filtering sequence, and then all I have to do is to compute the convolution of the sound signal with my filter. Since it's going to create samples that are very big in their magnitude, that's going to distort the sound a lot. So I'm dividing by 100 because, as you can see, the convolution filter is quite large. The values are quite large, so they're going to multiply the sound samples by large values, and that's going to create a distortion when I play it back. So I'm scaling it back so that we can actually hear the signal without distortion. So if I evaluate this convolution and create a sound object,
Houston, we have a problem.
and play it back, that's exactly the same signal that I received when I used the fast Fourier transform to filter
Houston,
it.
we have a problem.
So we can do the filtering with plain with Fourier transform. We can recognize the frequencies using the discrete Fourier transform, or we can use convolutions to achieve same effects. And as I said, convolutions are computationally a lot more efficient because instead of computing the expensive operation fast Fourier transform, all I needed here is to have about 150 samples of my filter applied to my 13,472 samples of my sound, and the convolution is computed correctly because, as I said, I assume that the rest of the samples are zero, so they're not going to affect the convolution anyway, whether or not I include them in the computation or not. So I'm going to end it here. I hope you enjoyed my little demonstration of the applications of the fast Fourier transform and a little exposure in the commands and the capabilities of Mathematica. You can play with different signals. Alright, this is it for today. Hope you enjoyed it, and I'll see you in our next video.